same as all the others. The main point, I have a few slides. I just want to go quickly through some ideas. So there's going to be a lot of stuff, but I just want to pinpoint to a couple of keywords here, okay? The first idea is, I showed you yesterday this kind of pipeline with different kind of stuff and said that kind of here we're in a good shape, we have good algorithm and good theory. I think, the theory here actually was a mixture of different things. Approximation theory and geometry, if you want, optimization. The last bit, perhaps the one that actually gained most attention, was statistical inference. Statistical learning theory, the whole theory of uniform law, large numbers and related ideas, connection with regularization, and so on. So, in some sense, I believe one move from here to here, some of these ingredients should have equal importance. And in some sense, we already heard about, so for example, Ben this morning was talking a lot about the geometry of the problem, some of the approximation properties, and there is optimization underlying everywhere. What about statistical inference here? Okay, and just this is my one super crowded slide on statistical learning theory. I just want to make 2 points. A, the classical denoising problem, you have noise, and then you assume you have some fixed points, okay? But in statistical learning, typically, the main concern is that these points, you don't choose them. They're given to you, and they're actually a cause of instability. You want to know how stable you are with respect to those, and that's overfitting, okay? And that's, it's bad even if you don't have the noise, okay? And because of overfitting more than other things, then you basically want to do regularization. Regularization works because you have some prior assumptions. You have to know how to explain smoothness and simplicity of the model. You're learning functions. And then you can answer questions like, okay, my algorithm will have some free parameters. How do I choose them? Theory, typically, I guess we can all agree, never gave particularly quantitative answers, but at least qualitatively gave an idea, should I pick this parameter as big as possible, or is there an optimal value, okay? And so it guides a bit how to use or develop algorithms in this context where what you're looking at is functions. So as we move towards learning representation, and again, I think what came out is that there are typically a couple of maps. One which is really the encoding of the data, an analysis kind of operation, and there is a dual decoding or synthesis kind of operation. And the novelty here, in say what Guillermo was talking about this morning, is that you don't try to only design this guy based on some prior information, but you try to adapt, the prior information to some knowledge of the signals at hand. So these are not just images, they are images of faces. Now I give you a bunch. The important bit here is this is just a reflection of a bigger word. That's what I was asking Ben, just to generate some discussion. I don't care about this 100 images. Who cares about these 100 images to some extent? I want to know something about the model that actually generate them, right? So this is a finite n. It's a problem for me. I mean, I would like to have n as big as possible. So how do we deal with that? Well, I don't know how do we deal with that. I can tell you one way people thought about this is, well, you would like a good representation. We discussed what's good. I think ideally we would like to have something that is able to discriminate signals. The problem is that if you don't have labels, what does it mean? I want to answer, I want something good for something I don't know yet. And what is typically done is replacing discrimination with reconstruction plus constraints, okay? And I'm not putting it out there as a good idea, I'm just, it's a fact that 90% of the algorithm, I think most of the dictionary learning point of view, as I'm going to describe in a minute, is reconstruction plus constraints. So this is my one way to describe this real quick. You basically, and this is also, I write in a slight way that is connected to the vector quantization point of view that was referred to before. You basically say, I have a coding. The way I judge it is through going back and decode things back to the original space and then judge how good this stuff are. This problem this is a matrix factorization problem once I write it in a more reasonable way. And it doesn't make any sense unless I make some structural assumption on the way the coding and decoding are done. And this is typically the way things are assumed to be. So-called the nearest neighbor coding, just basically solving an optimization problem for a given D, and then the problem of learning D, which is in this case linear and just a dictionary. So this is the matrix factorization problem. Here there is a question about how stable this is if X is noisy, how can you do this kind of computation, does it converge or not, what about the optimization, what are the different properties, and that's not what I want to discuss. Just point out that a lot of stuff is in this model, okay? You can describe most things. The list here is partial, but it can much longer. So one question is, what's not in there? Is there anything interesting which is not described here? But my point is, again, this is just, the way when statistical learning starts is basically by saying that you don't care about this. This is just empirical error. Who wants the empirical error? You actually would like to do something more expected error. And so ideally, if one question is perhaps you would like to replace this functional here, it kind of is expectation with respect to the distribution that you don't have, right? But is this a good idea? Okay, that's going in the direction I want to point things, but I'm raising there as a question. Is this the good thing to do? Okay, to go look at this kind of object. For sure, I can look at stability of this when I replace, the true distribution with the empirical one. But for example, can I develop a theory that is going to tell me how to choose the parameters in this model? I mean, Guillermo had lambda, and he has to choose. One thing is so the size of the dictionary. Can I develop some kind of theory that will allow me to say, how do you pick the parameters in this model when you have data at hand?
So I just want to make a clarification.
Yeah.
So information theory has been extremely successful. And information theory, there's two concepts which are related. I call it universal modeling, and that's related to MDL. And those parameters don't exist. If you look at the theory of information, we have done it and others have done it. So we always write it down, but if you formalize that through universal modeling and information theory, those parameters don't exist. That's one way to get rid of them. And then there is another body of people that are the Bayesian people that say you just put priors on those parameters.
Yeah.
But if you just want to formalize that as an MDL problem, those parameters don't exist. They come from the universal modeling in information theory, and they explicitly come out from the theory.
I guess in both cases, so the first case I'm completely ignorant about, and one reason why I'm saying this is to, now that I know I can learn about it. The second case, I think in both cases the question is, okay, but tomorrow we're going to run sparse coding and we have those parameters, okay?
You do have them.
And how do you choose them?
You don't choose them. They come from. Okay, we can. Sorry,
yeah.
I'm taking off your.
I don't know who's. I know I have an MDL friend that's going to tell me. I would like to know somebody actually choose 100 or. Sorry.
I can tell you exactly what I mean.
Okay, so I think that's that's one thing I want to discuss. The classical way you would do in statistical learning theory is try to develop a theory that tells you how far this is from something ideal, and then see what's going on. Okay, and here. This is some of the important part I want to show you. I just want to point to a couple of things that we did that are related, say, perhaps also to the Bayesian point of view, and say perhaps a nice way, an object of interest here is the distribution generating the data. Is this related to anything I just said? Okay. And so I have to introduce a couple of things. So one is whenever you have a decoding map, it means that you first map all your data in some space and then you decode back. And it means that you're actually getting a new distribution, which is the one that you obtained by running these two processes. If this is an identity, you did nothing. But if it's not an identity, it's a new distribution. Okay? And one thing which I didn't know and I found curious was it turns out that there is a result in vector quantization that can be generalized quite a bit, and it's not too easy to prove, that basically shows that whenever you're looking at this quantity, you're actually looking at the distance of the true distribution towards a new transform distribution with respect to a specific metric, which is an optimal transport metric. For you who are familiar with Earth mover distance, that's basically what this is. Okay? And when you replace this measure with the empirical one, you're basically saying, okay, I'm going to try to get to the empirical measure. Okay? And so if it's a good idea to look at this, perhaps even without knowing, when we're looking at this reconstruction framework, we're actually looking at optimal transport metrics as kind of a good idea. Why? Because in some sense, there is a nice computational framework for it. If I give you any metric here, I might not have an easy way to optimize these kind of distances. Here I do have it. And then, putting a nice table, which I think, I'm not sure how misleading or deep it is, actually start to make a parallel between the kind of objects. You have a regression function here, you have a measure here, you have some metric here, you have another metric here. Then you have representation of metrics so that you can actually run, say, constraint optimized algorithm. Okay? Again, the last two slides are more advertisement or just a possible entry point to the kind of question. And the point I want to make here is that we need a lot of theories, but we also need, I think, perhaps a statistical theory of what this stuff is doing, which is lacking so far. And perhaps the last couple of slides suggest that we want to go from approximation of functions, which is a subject we've been studied, in all kind of way, to approximation of other objects, perhaps spaces of measures. And this goes in the direction of, for example, quantization and information theory, okay? And then I think, I'm puzzled because as I move to function, to this kind of stuff, everything I know starts to be fuzzy. For example, one thing that bothers me is overfitting a problem. Okay, how much overfitting is causing about is? Can I get around? How much should I worry about this? I'm not completely sure. A lot. Yeah. Yeah. It's. Well, I'll leave that for discussion. Another thing is we discussed quite a bit. What kind of? I mean, here I can tell you smoothness. Okay. What kind of structure are interesting here? Ben gave us a nice good list. Okay. Other people will think about manifolds, for example. We say union of subspaces. We're discussing with Stefan quite a bit what's a good point of view when you have high-dimensional data. Okay. I don't know what are good kind of model. And then in the end, I think this, other things might be interesting, like incorporating symmetry, invariance, and so on. So I finish before I get a ball in my face. Okay.
We should do that in the middle of the time. Thank you, Lorenzo.